I'm just going to try and give y'all a few hints and informations to help you with some of the questions on the circular motion assessment list. And this is going to help with, I think it's like the last four questions, 4 or 5. Okay. I'm not going to work all of them, but I'm going to give you some information that will help you um, definitely with getting started and hopefully with figuring them out. So let's first talk about cars. Cars on a horizontal curve. So this isn't like the banked curves that we talked about. This would just be like a car going around a flat horizontal track. Okay, so here's my track. Here's my car. So remember, I've got acceleration and net force pointing in towards the center of this track. Okay, my car's going around this track with a velocity. If I look at it from the front, like so the car is coming at me head on, okay, my car's not moving vertically, so it's got a force of gravity, it's got a normal force, they're balanced. And then towards the center, we've got a force of friction. That's a static friction between the car and the road that's keeping it on that track. Remember, we said that if we didn't have that friction, he could just be in a constant velocity motion, or that's what he would want to be in. He wouldn't be able to continue going around this circle. He'd just be like, okay. But because there's that friction between the tires and the road, it's keeping the car on that circular track in that circular motion. So remember that with force of friction, we've got an equation, we've got a coefficient of friction, that's the mu, that's just that number, that unitless number that tells us about the interaction between the object and the road or the surface, okay, road in this case. And that's multiplied by our normal force. Also remember that in this case, our normal force and our force of gravity have the same magnitude. Okay, they're equal to each other because we're not moving up and down vertically. Okay. And then also remember that this force of friction, okay, this force of friction is our F net here, which is also our centripetal force. So when we're thinking about circular motion, our F net equals MA is F net equals M times V squared over R, because that's our acceleration, is V squared over R. So our F net is our vector sum of our forces is equal to mass times velocity squared divided by radius when we're talking about circular motion. So here you can also say that this is equal to mv squared over r. Okay. So if you're trying to solve for something like velocity, okay, if you didn't have that, or if you didn't have mu and you were given other things like the radius of the track and the mass of the car, then you could use those things to help you get other things just by remembering these relationships here. Okay, what is force of friction equal to, how normal and force of gravity relate to each other, and then remembering that this is basically our F net, our centripetal force. So this is our vector sum of all our forces that are causing our object to accelerate, and that's equal to mass times acceleration, which is our v squared over r. Okay. Okay, so take that, look at your car problems, see if that helps. All right, and then I'm going to talk about the Gravitron for a minute. So this was the the ride that we talked about where you end up being stuck to the wall while this cylinder is rotating you around at a really, well, not a really high, but high enough to keep you stuck to the wall, a high rate of speed. So this is a Gravitron ride. So when you're spinning, so we'll put an arrow here so we know that we're spinning, okay? In the Y direction, we're stuck to the wall. So we've got a force of gravity pointing downwards. We've got a force of friction. Again, that's a static type friction pointing upwards, and those two are equal to each other because we're stuck to the wall. So we're not moving up and down. In the X direction, we've got a normal force from the cylinder, okay, from the wall of the cylinder, pointing towards the center of the circle. So normal force here is our F net, or our centripetal force. That's what's actually causing us to stay in circular motion. If you took that away, like we did with the ball and the hoop, then we wouldn't be continuing in that circular motion anymore, right? So again, with this one, we can kind of set some things equal to each other to help us out, right? So remember that friction is the same as mu times normal force, and that equals our force of gravity. Mu times normal force could also equal m times g, if we wanted to remind ourselves what force of gravity is. And that's in our y direction, okay? So those are equal to each other. In our x direction, we've got normal force equals mass times velocity squared over r, because that is our net force. That is our centripetal force acting on our person who's spinning, okay? Notice here that you've got normal force on both sides, okay? So if you needed other things, for example, you might try solving for normal and setting these two equal to each other. If you don't have mass, you might do that and see that you don't need it because it would end up on both sides. Okay, so again, I'm not going to go too much further here just because I don't want to do the entire problem for you. But I think that might help you out in terms of solving for something. You could use this to help you solve for velocity if you didn't have it, or mu if you didn't have it. And remember, two more important points I want to make here. Velocity equals 2 pi r over t, where t is our period, or 2 pi r f. Okay, so if you're given the frequency or the period of the ride, so like how much time it takes to complete a spin, that would be your period, or how many spins does it complete per time period, that would be your frequency. More likely that you'll be given it in terms of frequency, okay? And you're given the radius, then you can solve for velocity. Put that back in if you don't have something else like mu, for example, okay? And then the last thing I want to mention is pay attention to your units, okay? Because we've done a couple of examples where you have to do some converting. You always want things in meters. You always want things in seconds. So you want your radius to be in terms of meters. You want frequency to be in terms of revolutions or cycles per second. Okay, so just watch out for things like that, where you might have to do a, like a quick conversion before you start with the rest of the problem. So, okay, so that's just a few things. Hopefully that will help you with, 2 or 3 of the problems on the circular motion assessment. And there'll be one more video about an item that's in a bucket being whirled around on a string. That'll be next.